All right, chapter 24. It's about geometric geometric optics. Now, geometric optics treats light as rays. So, all of our pictures of light will just be straight line rays of light that are either reflected or refracted from mirrors or lenses. The first section deals with plane mirrors. Those are just flat mirrors like you would find on your bathroom wall. Try to keep these lines straight. It's really hard on this tablet. So let's suppose that's our mirror. And I'm going to draw another straight line this way. That straight line is called the principal axis. And yes, it is spelled P-A-L, like the principal of your school. Principal spelled this way means primary. So there's our principal axis. Here's our mirror. And we have some object. I will let the object be a purple arrow. Let's see. All right, so how does a plane mirror form an image? Well, let's consider what happens when a ray of light from the tip hits a mirror. If that ray of light is coming in parallel to the principal axis or perpendicular to the mirror, it will simply hit the mirror and reflect straight back out. Now, if we think about some observer who's over here looking, here's my observer. My observer always looks like an eyeball. It sees that ray coming out, but it looks as if it could be coming from back here somewhere. All it knows, the brain just sees a ray coming out. What if we have another ray, also off this tip of this thing? Perhaps we have a ray coming in something like this. It hits here. Remember the law of reflection, the angle is going to be the same. I drew that little arrow 4 units tall on this graph, so 1, 2, 3. So it's going to reflect like this. It's hard to draw it perfectly. Again, your eye sees that ray is coming from back here somewhere, and it's really hard to get this perfectly straight. But that's where that ray appears to be coming. It was coming in. We could draw another ray. What color have I not used? That's coming in a slightly different angle off that tip. It was something like right here. It would hit. It would reflect back here. And again, if we follow all of those rays, they actually converge right here at this point. Your eye sees these rays coming out of it as if they're coming from this point right here. So we form an image. Does everybody see that? I know it's a little messy. You can see there's a blue ray coming out. I've got this violet ray coming out. I've got this green ray coming out. But your eye says, where are they coming from? And if you follow those straight lines back, they all appear to be coming from that point. So that's where we see our reflection. All right. Some things that we can notice about this reflection. First of all, this is a virtual image. Why is it a virtual image? Well, images come in two types. They come in real or virtual. In a virtual image, there are no actual light rays coming from the image. Your eye followed those rays back. Your brain backtracks them and thinks they're coming from here, but there's no light ray back here. This is what we call the dark side of the mirror. There is no light back here. So that is a virtual image. The other thing we notice about the image is the image is upright. Virtual images are always upright. We'll also notice that for plane mirrors, the image distance is equal to the object distance. Well, the magnitude of the image distance is equal to this distance from here to here, the object distance. Our book uses an S. Some books will use a D with a little. So, object distance the symbol for the textbook uses is an S. The symbol that your lab uses is actually going to be a D with a little O. Both of those are very common, so you might as well be familiar with both. The image distance is the distance from here to here. Our book uses S with a little prime on it. Some books will use a D with a little lowercase I for image. Okay, for plane mirrors, S is equal to the negative of S prime. Now, in this case, S prime is going to be a negative number. We need to have some rules for when object and image distances are positive and when object and image distances are negative. Sign rules, when things are positive and when things are negative, are going to probably be one of the biggest headaches in using the lens mirror equations. The equations are easy. It just takes a little time to sort out whether the object or the image, most of the time our objects are going to be at positive distances. but it's at a positive or negative image distance. So here's our sign rules. I'm only going to write it one way. You can assume then the opposite will be true. Okay. Object distance is positive when it's on the side of the incoming light. You can notice in this example that I drew up above, that's going to be the left side of the mirror, or what we call the light side of the mirror. Okay, so as long as the object's on the light side of the mirror, obviously you wouldn't put an object behind a mirror. So object distances with mirrors are going to always be positive. These same rules are going to apply not only to mirrors, they're going to also apply to lenses. And so lenses, you can see how you could put it on either side of the lens. Image distance is positive when it's on the side of the outgoing light. Well, for this particular situation, that is still on the left side of the mirror. So in the above example, you can see that S prime is, since it's on the dark side of the mirror, there is no incoming light or outgoing light. Or if you're thinking mirrors, there's no incident light and there's no reflected light. So behind a mirror is always going to be a negative image. In front of the mirror, you are going to have a positive image distance. And you can form images both behind mirrors and in front of mirrors. Now, for a plane mirror, those distances are always going to be equal, except for the sign. One will be positive and one will be negative. Let's take a minute and let's talk about magnification. Plane mirrors do not cause magnification, but our definition for magnification, or the equation used in this book, is image height over object height. Okay, our textbook uses y prime for the image height and y for the object height. Other textbooks and your labs over this is going to use HI for image height and HO. I found those a little more intuitive, but they both work. M is positive when the image is upright. M is negative when the image is inverted. we can tie that into what we said earlier. Upright images are always virtual images. Inverted images or upside down images, we're going to find out, are going to be real images. And we'll look how we can form some of those. So, for a plane mirror, for a plane mirror, M is always equal to 1. A plane mirror always forms virtual, erect, and sometimes I use the word erect. More often lately I see them use the word upright, reversed images. And the only part that we haven't talked about is what does it mean that it's reversed? We know what it means that it's virtual and upright. Reversed simply means the left hand appears to be a right hand. So if you look at yourself in a mirror, your left eye appears to be the right eye of the image. Okay? That pretty much takes care of everything to do with plane mirrors. The image drawing is probably the trickiest part, but we only use the law of reflection. Whoops. That blue line went in parallel to the axis or perpendicular to the mirror, so it reflected straight back out. The green line, we used the law of reflection, and that violet line, we used the law of reflection. And you see when we follow those back, all of those rays appear to come from the same point behind the mirror. We use the tip of the arrow, but we could use that for any point on that arrow. Those same things would happen. All right, so and the only other thing we really want to stress, we have a couple of formulas. Well, really, so far we only have one formula, and that's for magnification. And we've got these important sign rules. The object distance is positive when it's on the side of the incoming or incident light. The image distance is positive when it's on the side of the outgoing light. Or if we're thinking of a mirror, that would be the reflected light. When we look at lenses, that will be the refracted light. So our one formula basically that we got so far is that M equals Y prime over Y, or HI over HO. All right, so moving into our next section, section 24.2, it deals with spherical mirrors. And we're going to use spherical mirrors. I believe the lab makes a reference to curved mirrors. There's actually another type of mirror that is curved that is better, and that's a parabolic mirror. Parabolic mirrors form better images than spherical mirrors, but we're going to talk about spherical mirrors. I'm going to start with the idea of a concave spherical Whoops, I left out a letter of sphere. Spherical mirrors. Okay. So a spherical mirror is curved. I'm not going to worry about drawing it perfectly. If we draw a line right through this, that line is called the optic axis or the principal axis. Both words are used. Because of something called spherical aberration, spherical mirrors are not perfect. So we're only going to look at relatively small radiuses of curvature. So we're going to treat this in a way as if, and this is, it falls on a plane. But of course we know it's actually slightly curved. But that would be, if we had a plane mirror, that'd be our straight line. All right. There, and I'm not measuring this, so we're just going to call the center of curvature is called C. And the distance from this line, this vertical line I've drawn, all the way to the center of radius is called R. That's the radius of curvature. The halfway point between C and R is called F. That's the focal point. I'll show you what, I probably should clean this up a little bit. So that distance, that point is C for center of curvature. And then this distance that goes to the focal point is called F. That is the focal length. So let's get some more vocabulary written down. C is, the center of curvature. In other words, if we drew the entire sphere or the entire circle, that would be the point at the center. R is the radius of curvature. Okay, R comes with an important sign rule. R is positive when it's on the side of the outgoing light. For a mirror, that's going to be on the side of the reflected light. If we're talking about lenses, it would be refracted. Because with lenses, we're interested in light passing through the lens. But when it's on the side of the outgoing light, R is positive. Oh, and I said when it's, I should be more clear than that. When C is on the side. So when the center of curvature, which is right here, is on the same side as the reflected light, which here again for a concave mirror, spherical mirror, we can think of this as being the light side of the mirror, and we can think of over here as being the dark side of the mirror. So for mirrors, incoming and outgoing light are on the same side. So for a concave spherical mirror, R is always positive. But a concave spherical mirror, R is positive. Okay. F is a point called the focal point. You'll see why it's called the focal point here in a minute. And it is located halfway between C and the mirror. And F is something called the focal length. That's very important in our calculations. F is exactly equal to 1/2 R, or R divided by 2. Okay? So if I have a concave spherical mirror, R is positive and F is positive. Some people will call these positive mirrors. Concave spherical mirrors are positive mirrors. Sometimes they're called converging mirrors. So what happens? Let's look at what happens if I have a concave spherical mirror. And again, I could do this a little bit if I wasn't working on a tablet where I'm looking on my screen and trying to draw a picture. So here's our mirror. Whoops. Let's suppose that this is our focal point. That means our radius of curve, or center of curvature, is about here. I'm not counting the squares, but I know F is exactly halfway in between. If we have beams of light that are parallel, any ray of light that is parallel to the principal axis coming in is going to reflect off that mirror in such a way that it goes through the focal point. So I have these incoming parallel rays, but when they reflect, they go, all of them go through, and it's really hard to, I'm aiming for it best I can, through the focal point. That's why it's called the focal point. The focal point is the location where parallel rays are focused. You can also think of why it causes them to converge. So we have two rules here if we were going to draw ray diagrams. Rule 1 is any ray parallel to the axis is reflected through the focal point. Now, you'll remember that light rays are reversible. I can go at this the same way. Here's our mirror, slight curve. Here's our axis. Here's my focal point. C's about here. And say that any ray that comes in through the focal point will reflect parallel. Well, remember, light is reversible, so that makes perfect sense. If parallel rays would reflect through F, then rays through F will reflect parallel. So if we have another ray coming through F, it will go parallel. So no matter at what angle, any ray coming in through point F will hit the mirror and reflect parallel. So any incoming ray through the focal point is reflected parallel to the axis. Statements 1 and 2 are that I just wrote are true they are absolutely true for parabolic mirrors. Parabolic mirrors obviously actually have the shape of a parabola, and they have one focal point. They're extremely precise. They are almost true for what they call paraaxial rays. Those are rays at small angles to the axis for spherical mirrors. Spherical mirrors have a problem they call spherical aberration. If you have a large enough angle, you'll find that they don't actually, the parallel rays won't all actually go exactly through the focal point, but we are going to act as if they do. So we're not going to get bogged down in this, but I want you to just know that there is a difference between a parabolic mirror and a spherical mirror, and that difference is something called spherical aberration. There can be a slight blurriness or fuzziness with a spherical mirror you won't get with a parabolic mirror. Now, so what are our equations? Well, the one nice thing about this chapter is the equation for mirrors and the equation for lenses is the same. And it's called the lens-mirror equation. And the lens-mirror equation says 1 over S plus 1 over S prime is equal to 1 over the focal length. We also have our magnification equation, which says M is equal to Y prime over Y, which is equal to negative S prime over S. Now, if you happen to be working in a different textbook, that equation might look like 1 over object distance plus 1 over image distance equals 1 over the focal length. And magnification might look like HI over HO, or negative image distance over object distance. Those are just variations on how they label things. I think you know what everything is. Let's quick review. S is equal to DO, object distance. S prime equals DI, that's image distance. Y equals HO, that's object height. y prime equals hi, that's image height. And f is equal to the focal length. And really important to know when you're thinking focal length, f is positive for concave mirrors. And later we'll learn that it's also positive for converging lenses. So we're only doing concave mirrors, but those two are positive. They can be called positive mirrors or positive lenses. Let's do a problem. This is an example from your text, I believe. It says a lamp is 10 centimeters, and I'm going to assume we've got 2 sig figs everywhere. They don't really say that we have. I'll go ahead and put extra there. 10 centimeters in front of a concave mirror. Which forms an image three meters in front of the mirror. Okay, that's not like our plane mirror, which formed an image behind the mirror. Concave mirrors can form images both in front of and behind them. So in this case, it's in front of the mirror. We have several questions. What is the radius of curvature? If the lamp filament is 5 millimeters tall, how tall is the image? And what is the magnification? Okay. Well, let's start with what is R. We know, what do we know? Let's write down everything they tell us. A lamp is 10 centimeters in front of a concave mirror. So they start off by telling me that the object distance is 10 centimeters. And the image distance is 3 meters. Now, our equation tells us, and I just used the wrong symbols, I'm so sorry. Those are used for height. Object distance is S, image distance is S prime. Our equation says 1 over S plus 1 over S prime equals 1 over F. If we find the focal length, we'll know the radius of curvature. But we need units to be consistent. So why don't we let our 3 meters be 300 centimeters? So now when we solve this, we got 1 over 10 plus 1 over 300 equals 1 over F. Calculators were made for this. 1 over 10, 1/10, plus 1 over 300. If you put that in your calculator, you're going to get a decimal, but remember, we want F. You're going to end up getting that 0.10333. The 3's repeat is 1 over F. but we want F. So we take the reciprocal of that. Use your calculator button to take a reciprocal. And we get that our focal length, F, is 9.68. That's too many sig figs. If we double that, then we get that the radius of curvature comes out to 2 significant digits to be 19 centimeters. It really came out to be about 19.35. Okay, so the answer to A is that the radius of curvature is 19 centimeters. The second question says, how tall is the image? Well, we have a relationship that says that y prime over y is equal to the negative of s prime over s. So let's fill in everything we know. We don't know y prime. Y is 5 millimeters. Now, S prime was 300 centimeters. We've got to have some uniformity here. So negative 300 centimeters. And S was 10 centimeters. Now, is it okay to leave Y in millimeters? The answer is yes. If we do, since this is a proportion, Y prime will come out in millimeters. If you're uncomfortable with that, you can change it to centimeters. 5 millimeters would be 0.5 centimeters. So if we'd rather be consistent, we could 0.50 millimeters. Centimeters. I changed it to centimeters. And now you just need to cross multiply. You see that y prime is going to come out to be negative. Negative 300 times 0.5 divided by 10. And it comes out to be negative 15 centimeters. So really big. C wants to know magnification. Magnification, remember, we can do 2 ways. You can say that M is y prime over y. So negative 15 centimeters over 0.5 centimeters. It's going to give me a magnification of negative 30. That means it's 30 times bigger, but it also means that it's been inverted. The other formula for magnification is that it is the ratio of negative s prime over s. So in this case, that would be negative 300 centimeters over 10 centimeters. But you see, that also gives us a negative 30. So it didn't matter which of those formulas that I used. So what does that tell us? Well, the fact that the magnification is negative tells us that the image, well, there's 2 things. First of all, the location of the image, which was given to us, is in front of the mirror. It's on the side of the outgoing light. So what we know here is that this image is real. And the image is inverted. Really knowing the fact, since this is negative, anytime it's negative, that tells you that you're inverted or upside down. Anytime you're inverted or upside down, you know the image is real. what does that look like, just roughly? So you've got this mirror over here. You've got this axis. And your object is only 10 centimeters away. Your image is way over here. And it's 30 times bigger. So I have not even drawn this close to being drawn to scale. But I just wanted you to see what happens. The focal length was right about here. Remember, we got that the focal length was about 9.5 centimeters and the object was at 10 centimeters. So when light goes in, picture a parallel beam coming in, and then it goes through right here. You can see it's going to go way out here. So I didn't draw this nearly 30 times bigger. Whoops. But you can see, but the light, my point being, that the light actually meets at this image. It's drawn terrible. Let me try to draw it a little better because I'm not drawing to scale because I really can't. But that reflected light, let's draw the image a little bit bigger because if this was too tall, this would have to be like 60 lines tall. See what, let's draw it shorter. So if the object's here and the focal point is right there, almost exactly by it, you've got light coming in here, but when it reflects through that focal point, it goes way down here. You end up with an object where the light all actually meets way down here. If we draw another one, another ray, same thing, it's going to come in, it's going to hit, it's going to reflect, and it's going to do the same thing. It's going to form an image way down here. I cannot draw it perfectly, so I'm not even going to try. Okay. This is a real image because the light is actually meeting at that point. Okay, so that's a concave mirror, also known as a positive mirror because it's got a positive focal length. Okay, the other type of mirror is the convex mirror. These are sometimes known as diverging or negative. If you have a convex mirror, it bulges out. So here's the principal axis. You can almost picture how light that shines on it, that's coming in parallel, it doesn't bounce back towards a focal point. If we used to use the law of reflection and we think of this curved surface, it actually bounces off something like this. It spreads the light farther away, not closer together. Well, the radius, the center of curvature, is going to be over here for this mirror. That means the focal point is also over here. And what in fact happens is these reflect away as if they came from the focal point. They didn't come from the focal point, but somebody over here looking might think so. So one of the things we want to remember for convex or diverging or negative mirror is that F and R are negative. The focal length and the radius of curvature. This should be a capital F to indicate focal point as opposed to focal length. In this case, light rays parallel to the axis reflect as if from F. They don't pass through the focal point, but they look as if they're coming. Or light rays toward F reflect parallel to axis. That's just the reversibility. If I have a ray and I say, look, this is an incoming ray, and it looks as if it's going right towards that focal point, when it hits it will reflect parallel because rays have reversible paths. So if a parallel ray reflects as if it's coming from the focal point, a ray towards the focal point will reflect parallel. The equations are exactly the same. We don't have any new equations. The only thing that's different that we really have to pay attention to is for a convex mirror, these are going to be negative. That's going to change things just a little bit. So let's do an example. This example has to do with Santa Claus. Santa sees his reflection in a spherical Christmas ornament. If you have a shiny metallic Christmas ornament, it acts as if it is a convex mirror. The ornament has a diameter of 7.2 centimeters. That means that the radius of curvature would be 3.60 centimeters. And then the focal length is half of that, would be 1.80 centimeters. But these will be negative because it is convex. That's going to be important that we get those dimensions right. They also tell us that Santa is standing 0.750 meters from the ornament. And that Santa is 1.60 meters tall. So we know his height. Let's locate the image. Let's talk about the magnification. Let's just find everything there is to know. So he's standing, this is telling me that the object distance is 0.750 meters, and I keep trying to use Y's for distance, and I should not do that. So maybe the D's would be better. That S, the object distance, and this would be the height, the object height. Okay, so our equation 1 over S plus 1 over S prime is 1 over F. In this case, we want to locate the image. So we have 1 over, and let's see, our focal length is in centimeters. So why don't we work in centimeters? So this is 75.0 centimeters. So 75 centimeters. I don't know this. The focal length is negative 1.8 centimeters. We've got to pay attention. Doesn't matter whether we use distances in meters or centimeters or millimeters, but they have to be the same. So now to calculate a question, I'm going to do 1 divided by negative 1.8 minus 1 over 75. And then I take an inverse. And I get that S prime is negative 1.76 centimeters. That means that the image is 1.76 centimeters behind the surface of the ornament. If we look at his image height, we know to get that we can use y prime over y is negative s prime over s. So we don't know y prime, but we know that he is 1.6 meters or 160 centimeters. The image distance is negative 1.76. So the negative of a negative, of course, is going to be positive. And the object distance was 75. So we can see that he's going to come out to have a positive height. So 160 times 1.76 divided by 75. And his comes out to be 3.75 centimeters tall. It is positive, which means that he is upright. Positive also means that it is virtual. Well, that makes sense because the image is behind the surface of the ornament. There's no actual light behind the surface of the ornament. If I wanted to calculate the magnification, I would simply put y prime over y. So 3.75 over 160 centimeters. And the magnification is 0.023. I actually get 5. I used an unrounded, but something like that. If you think about it, here's Santa. Santa's kind of chubby. And here's the ornament. And then he looks, he sees a little teeny tiny version of himself inside the ornament. So he's standing 75 centimeters in front of the ornament, but he sees a little bitty image of himself that's 1.76 centimeters behind the ornament. Okay, so those are our 3 types of mirrors. Since we didn't have class this morning, I'll probably go ahead and work another problem or 2 besides these examples. Let me look in the book. So, looking in the book, chapter 24. let's do number 8 because you can do number 5 yourself and check it. So number 8 says a concave mirror has a radius of curvature of 34.0 centimeters. So first of all, they tell us that it's concave. Those are the mirrors that look like, that look like this. They're also converging mirrors or positive mirrors. And they tell us that the radius of curvature is 34 centimeters, which is also telling me then that the focal length is a positive 17 centimeters. I know it's positive because it's concave. Question A, what is the focal length? So we've already answered that, 17 centimeters. B says a ladybug that is 7.50 millimeters tall. So we have a ladybug. It has a height, I'm going to use both, of 7.5 millimeters. And it's located 22 centimeters from the mirror. So its position S, or its object distance, is 22.0 centimeters. Find the location and the height of the insect. So location and height of the insect, 1 over S, 1 over S prime. Did I read that question? Find the location and height of the image. Okay, correct. I want to find the image. I know where the insect is. Equals 1 over F. So S is 22 centimeters. The image distance we do not know. The focal length is 17 centimeters. So I'm just solving this for S prime. 1 over 17 minus 1 over 22. Take the inverse, or the reciprocal, and I get that the image is at 74.8. What's next? The height of the image. To get the height of the image, we know that the height of the image over the original height is equal to the opposite of y prime. I'm going to have S prime over S. So the ladybug was how tall? 7.50 millimeters. I can't leave that in millimeters. That will just mean y prime will come out in millimeters. This will be negative 74.8. S was 22. Notice the ratio. It looks like it's going to be a little more than 3 times larger. It's also going to be negative, which means it's going to be inverted. So if I solve this, 7.5 times 74.8 divided by 22, I get that y prime is negative 25.5 millimeters. They don't ask me for magnification, but magnification is easy to get. It is the ratio of image distance to object distance. So negative 74.8 over 22. It's negative 3.4. Notice that means that it's upside down. This is a real inverted image. Inverted is always real. Concave mirrors can form real images out in front of the mirror, and a lot of times those are magnified images. Okay. Part C just asks the question on that. If the mirror is immersed in water of refractive index 1.33, what is its focal length? The focal length of a mirror only depends on the radius of curvature of the mirror. It does not depend on any of the medium around it. So there's nothing, no change. Let's look at number 11. Number 11 looks trickier. And that'll be our last one. Number 11 says a coin is placed next to the convex side of a thin spherical glass shell having a radius of curvature of 18 centimeters. An image of the 1.5 centimeter tall coin is formed 6 centimeters behind the glass shell. Where is the coin located? Determine the size, orientation, nature, real or virtual of the image. So, first of all, it's acting like a convex mirror. It's curved outward. That tells us the focal length will be negative. It gives us some information we're going to need. It says it has a radius of curvature of 18 centimeters, so the center of curvature is over here. So R is actually going to be a negative 18 centimeters, and the focal length is going to be negative 9 centimeters. An image of the 1.5 centimeter tall coin is formed 6 centimeters behind the glass shell. So they're telling me some more information. They're telling me the image position is negative 6 centimeters. Remember, for a mirror, this side is light and this side is dark. And any distance on the dark side is going to be negative. All right. They also tell me, and I wrote it again, I don't know what my problem is. This is S. They told me the location of the image. Then they also told me the height of the image. Nope, they told me the height of the object. The height of the object is 1.5 centimeters. Then they ask all kinds of questions. Where is the coin located? Determine the size, orientation, and nature, real or virtual, of the image. So let's see if we can get all of this figured out. First of all, if the image is behind the mirror, which they've already told us, I already know this is going to be a virtual image. Virtual images are always upright, so I have some clues already. But let's find where the image is located. 1 over S. I'm sorry, where the object is located. 1 over S prime, 1 over F. I don't know where the coin is, but I know the image is at negative 6 centimeters, and I know my focal length is negative 9. So that's going to be negative 1/9 plus 1/6 when I'm solving this. Take the inverse, and I get that S is 18 centimeters. So the object is located 18 centimeters in front of the mirror. Let's look at the size and orientation of the image. We know that y prime over y equals s prime over s. The original height, the object, is 1.5 centimeters. The image is -6 centimeters. Wait, this is negative. So negative over -6 is going to be +6 centimeters. And S was 18 centimeters. So the image distance was negative, but the formula for magnification looks like this. If we want to know y prime, it's going to be 1.5 times 6 divided by 18 is 0.5. So it definitely did not act like a magnifying glass. It made an image that was smaller. As far as the type, the image is upright, which means it's virtual. So it's 0.50 centimeters tall. It is upright, and it is virtual. So it's like looking in a mirror and seeing a little teeny tiny image of it behind the front surface of the mirror. I'm going to do a quick check, make sure we got all those right. "18 centimeters from the vertex, 0.5 centimeters tall, upright, and virtual." We got it perfectly right. This feels like a good place to stop. We can answer questions when I see you again on Tuesday.